sort of everything you want to know about quantum computing, but was afraid to ask. All right. So, yeah. All right. So I've done a lot of things. I'm not going to bore you with all those things right now, but I will tell you. So I used to give away books, and I realized that's such a waste of everybody's time because people don't read books in general. So now I sell them. You know, so, and I sell them at cost, but like, I'm not trying to make money. I just don't want to give books to people that don't read them. So my wife's out there. You know, we got some bundles. The two books that I'm sort of recently did, History of AI is my last book, and I did a book about Dr. Deming. And if you were here last year, we really focused on Deming days, so that was kind of cool. All right, so don't try this at home. No cats were harmed in this experiment. But more importantly, I'm not a quantum expert. I'm not actually a scientist. I decided last summer I was going to write a book about the history of quantum computing, and my first sort of fear was, am I smart enough to do this, right? And I think the answer is maybe I'm not smart enough to do it, but I'm brave enough at this point. So I've learned quite a bit about it, and you're sort of my guinea pigs, right? Like, you know, if you all tell me I was terrible, then I'll maybe rethink another book. But if this one works, you know, then hopefully that I'm on the right track and I can finish this book. But I will tell you, quantum is hard. It is really, really freakily hard, right? So I want to start off with the state of quantum computing right now. And so I wrote an article recently that basically said that, like, yeah, it's not moving too fast, but it's sort of scary, but it's like we're in this really weird hype cycle where there's incredible stuff happening in the lab. But it is in the lab, but it's pretty incredible. You know, it's kind of like reading Mythos, right? Like there's some scary stuff in those system cards that tell you like all these things that could happen, but they're not happening at JP Morgan Chase, right? So a weird analogy, but if that makes sense. It makes sense to him, right? So, but so there's this idea, and we'll get into qubits in a little bit, but you know, the qubits are sort of a kernel part of quantum computing. And I think one of the things that you can look at, like this lab things. So I went to an IEEE quantum conference. So I was, all right, this summer, should I do this? I started doing some research. I went to my first quantum conference, and it was mind-blowing to talk to some of these scientists that won Nobel Prizes. And you know, so basically the story is that this idea of like Q-Day or this quantum supremacy is theoretically 1 million qubits, and again, if you don't know qubit, hopefully I'll solve that in a few more slides, at a fault-tolerant 1 million qubit machine. And that's the machine that will basically do these intractable algorithms, right? Can we get there? You know, the running joke is it's always 5 years away, right? But here's some data points. It was in 2023, the estimate was 6 million. At the end of last year, it was 1 million qubits. And now they're sort of saying it's 500,000. Right? So, like, there is progress, and there are some big dollars being spent, not here even. Like, if you look at the chart of how much they're spending in China, it will really freak you out. But, by the way, Google, Microsoft, and IBM are pounding away at this. And this is the one that sort of freaked me out a little bit. Again, it's the lab, so don't panic, don't sell all your Bitcoin just this moment. But Google proved theoretically that, and I'm not a crypto expert, but basically Google, in a simulated lab, that they could beat the 10-minute hold. So if you're selling a Bitcoin, the coin, there's a 10-minute hold. The assumption is nobody could actually break a 256 SHA in like years, let alone under 10 minutes. They literally proved that they literally could do that, again, in a lab. They used the Shor's algorithm, which is sort of, I'm not going to get into that, but you know, yeah, it's enough. I asked one of my friends had a quantum company for 10 years. And I always ask him, is it real yet? Is it real yet? Not yet, not yet, not yet. And then on this one, he's like, it's not real yet, but, yeah, so, but here's the thing, right? Like, everybody's freaking out about crypto, and rightfully so, right? Like, you know, can you break RSA? So put it this way. That 256 SHA is going to be broken in my lifetime. I think it's within a 5-year window. It's less than 10. Hopefully I live that long. I'm old. 496 ain't happening in my lifetime. Right? Those two, I'm fairly certain I'm correct on both of those statements. right? So, but what gets really interesting is the optimization. The most fascinating part that I had at the IEEE conference was not, I stayed away from the crypto ones. Like, there's people way smarter than me working on those problems. People have to protect banks. But the really interesting stuff start happening when you start solving I'm an entrepreneur. I've started a lot of companies in my life. I sold companies. I've moved into the basement of my brother-in-law's house because I've lost some companies. Speak to my wife out there about this. So I look at the entrepreneurial spirit and I think, man, there's going to be IP. There could be this universe where people get patents on algorithms that solve these intractable problems. That's fascinating. And these problems are drug discovery, real protein folding simulation, not sort of like deep mind stuff. And I'm not trivializing what's going on in deep mind, but one of my friends, my sort of mentor in quantum, says, John, imagine they invent a new kind of plastic. I mean, most of you are young, these are things that may happen in your lifetime, right? Or if you've ever heard of Citadel, right? There's sort of the amazing, imagine one person sitting in front of their own computer and have the power of Citadel, right? Or imagine, the traveling salesman, but like, imagine you figure out the algorithm of how to take off planes. And if everybody talked to Paula Thrasher last night at dinner, right? She works with Leidos, right? That's a problem they're trying to solve with deep neural networks. Getting planes efficiently land, and like it's hundreds of millions of dollars. And so again, take this slide with a grain of salt. It's theoretical, but so I did some mapping. I've talked to some experts. Mileage varies. But like a penicillin simulation, which is, for like a sort of a simulation, it's sort of easier. With a classic computer, it'd be billions of years. The theory is when we hit that, whatever that sort of mythical supremacy is, it's going to be weeks. The knapsack thing is like a baby version of the traveling salesman, right? Like it's used a lot in sort of quantum proofing or kind of standing is you take a bunch of elements in a backpack, you got to fit them in perfectly, size, weight, and all. That's an intractable problem. That's a billion-year classic computer problem. Weeks, right? The RSC-248, again, mileage varies. 30K, only 30,000 years, not a billion, right? But in a quantum simulation, it's hours. And then one of the things Google uses a lot is random circuit simulations. Think of it as a slot machine, where they compare how quick you can get to mirroring randomness, which sounds horrible, but how does it compare? And this is one that alarmed a lot of people. So they had a 10,000 estimate year on a classic computer and did it in 200 seconds. So there's a paper on that last year. So that's the world right now. It's a little scary. I wouldn't lose sleep tonight on it, but what I would do, and I'll end the presentation with this, I would start, if I'm an organization, I wouldn't ignore quantum computing right now. Not for the crypto, but the optimization options. I mean, you want to be the first airline to get the patent on, if this comes true, on how to efficiently land and take off planes. That would be kind of a toll booth for every other airline, right? And here's the one last thing about this state of it. Its name of what they're calling the state of quantum computing is an apology, right? It's a noisy, the sort of noisy intermittent scale quantum, because this is the problem. This is the $1 trillion opportunity, because it isn't so much how many qubits, it's how much can you create a fault-tolerant machine. Because, by the way, not only dust disrupts quantum problems, like dark matter matters, right? So this is a hard problem, right? So what's in the box, right? This is the part that I figured, let's use this. Everybody wants to know the sort of the story of the box. So all right, there's a box, right? And they asked Schrödinger's cat, right? They asked Schrödinger's daughter, what was the deal? Why a cat? And she said, I think my dad really didn't like cats. So if you're a cat lover, I hate this because I'm a dog lover. Think of it as a puppy. All right? But you have this cat on the right-hand side. And then you have this radioactive atom on the left-hand side. And radioactive atoms decay, and they randomly decay. So they could theoretically be an hour, they could be 10 weeks, they could be 100 years. So there's this randomness. And then there's a detector that says, when the atom decays, I'm going to spill this poison vial, and the cat dies, right? That's the experiment. That's what's in the box. Now, why did Schrödinger do this? Well, so what happened is, like, a couple of people invented quantum computing, spent their rest of their life trying to debunk it. Or not quantum computing, sorry, quantum mechanics. And be really careful, so quantum computing doesn't come along. These are quantum mechanics. And he, even though he invented, and we'll see in a minute, he created the wave function, he created the Schrödinger equation, he just, this doesn't make sense. There's got to be something. And he wanted to basically magnify, to show the absurdness of what he and a couple others have sort of invented or discovered. So he basically put this, magnifying glass to say, if the micro world looks like this, what would the macro world look like? Right? And we'll go through these components of why it gets weird, but this is what his motivation wasn't to say, hey, this is an experiment that proves quantum mechanics. It was an experiment to say, there is something wrong here. And I'm not feeling comfortable with what I helped create. And so, so the cat wasn't the point. It was this, what we're going to talk about is the measurement problem was the point. So, like I said, he invented wave mechanics. He did the famous Schrödinger's, so again, he's a guy that is pinnacle in the sort of thread of quantum mechanics. There's a couple other people that came before him, including Einstein, which, by the way, Einstein went to his grave kind of frustrated that this thing existed and they couldn't explain it. But it all comes down to this sort of two worlds, right? There's sort of these, there's a world in the subatomic that sort of works in this way that is really weird. I won't get into Heisenberg's uncertainty principle, but it's this idea that a particle is in multiple places, right? And so it has more than one state. How can that be, right? And then when you look at it, or you observe it, or particularly when you measure it, it collapses into one state. And this is sort of where it gets really weird. And there's a couple other weird elements as well. And so if you think about 2,000 years of how humans interpreted motion, from the original humans of up, down, left, right, forward, backward, from sort of Aristotle to sort of Galileo to Kepler, and then ultimately Newton, it seemed pretty logical. I mean, Newton should drop the apple, it hits the floor. And all of a sudden, in the 20th century, a bunch of these people are saying, you drop the apple, it may not hit the floor. Or it's not going to be right there next, as the ball rolls. It's somewhere in this weird wave. It's in multiple places. How can that be? How can a ball be in multiple places? And again, Schrödinger's cat is why we can observe it at the subatomic level and it looks like this, and we try to make sense of it in the real world. It doesn't make any sense. So the crash course. So the thing I love about what I realized, I was doing all this hard work to try to explain Schrödinger's cat there, or not trying to explain quantum computing and quantum mechanics to people. And I was on a podcast with a friend, and I just happened to mention I'm writing a book about the history. John, can you explain Schrödinger's cat? And I'm like, oh man, really, right now? Okay. And I did it, and then I realized he was fascinated. It was Josh Long, right? One of the most premier Java developers on the planet. And he was just giddy that I explained it to him. And I told him, I wonder if everybody else would get giddy if I explained it through this. And then as I dug deeper, I realized it's the perfect crash course. So what I will tell you right now, if AI makes sense, B, you understand what I'm making sense of, that you will probably, after this presentation, if I succeeded, know more than 90% of the people in Atlanta or in this area about quantum computing. And there's three things you need to remember. You remember this idea of superposition, entanglement, and measurement. If you walk away with those three things, you can walk into a party and say, hey, what do you know about quantum computing? So the superposition is the one that sort of drove Schrödinger crazy, right? Not crazy, actually, but there's a history of people all these people that were sort of on they had to have an ontology for this. They're on their deathbed is, damn, I wish I would have never gotten into quantum, right? But the superposition is that an object can be in multiple places at one time, right? And so the Schrödinger's cat example is Not that we don't, it's real, no, John, it's probably the cat is dead and alive, right? No, like, I get what you're saying, John. The cat is actually dead, but until I open the box, I don't find out. No, it's not that. It is actually dead and alive, right? And that's the sort of weird thing to sort of give into, that these things have multiple, sort of multiple states, or what they call superposition. And again, it's not hidden. In fact, Einstein sort of had this, there has to be a hidden variable. There's something that, he said, God doesn't play dice. So again, his whole life was literally, I can't accept that there's something that we're not seeing. And so what I like to use is, and again, a lot of these analogies kind of suck, but they're really good. And like this one, you sort of get yelled at by quantum physicists when you use it, or quantum mechanic experts, but it works for me, and I think it will hopefully work for you. It's the coin flip. So when you flip the coin, it's not heads and tails, or tails, it's both. It's spinning. And it's not till you like catch it and put it on your hand or drop on the floor, it goes to one discrete position. I mean, that's the Schrödinger's cat. Schrödinger's cat is the cat is both dead and alive. You open the box, you kind of find out what it is. And so, but this is where you literally start getting into where quantum computing starts to work. Right? In quantum computing, we have this idea of, in classic computing, we have bits, right? We expect a bit, it's on or off, and or if statements, all that stuff is Boolean logic, right? But basically, when we get into the quantum world, we create these things called qubits, and they can have multiple states. So now you can sort of build algorithms about this capability that has multiple states. And so think about this example, right? Is that if you had 2 bits, there's 4 possible positions, but there's only one that you inspect at that time, right? Like it's going to be 01, it's 00, 01, 10, 11, right? That's it. But in a quantum, you had 2 qubits, it's all 4 positions when it's in the superposition, right? And so if you sort of play that out, like I think like mostly if you've done any assembler coding, or which I have, but it's like a 32-bit is like a 4 million number, right? If I needed to calculate that, it's going to be one number. Like the whole long bytes and all that are going to equal sort of one large number. If I have to calculate that sequentially or through parallelism or even multiple matrification, it's a step function. But the idea of that being 32 qubits is that it's actually all 4 million positions at once. And so hopefully it'll get a little better at explaining this, but that means I can, instead of inspecting one sort of state, I can inspect all 4 million of those states in one fell swoop. And this is how you get, foreshadowing to solving intractable problems. Right? And so what's going on right now is that there's a bunch of different ways people are trying to solve this. The 3 most popular, the superconductor, so IBM and Google, these are like paired copper pairs where they literally behave at the microscopic level, quantum behaviors. And they have to put them in there was a guy there, a sales guy from like one of the quantum companies. He says, I'm the most expensive refrigerator salesman there is. Because these are the ones you have to put in 450 below 0 degree. And then not so much for the conductor, but it's for the noise. You need to eliminate, remember that noisy stuff. And then there's trapped ions with like lasers. IonQ is probably a leader there. And there's a really fascinating company called PsiQuantum that's doing photonic stuff, and that's room temperature. So there's all these sort of trade-offs. So, and then, all right, so that's superposition. That's your Kurzweil, that thing can be multiple positions, that maybe really large qubits can have lots of positions to interrogate at one time. Entanglement is that multiple particles can get in this, what they call entangled state. So again, taking it back to the Schrödinger's cat, the radioactive atom and the cat are entangled. In fact, that whole thing is entangled. Right? Again, this is sort of like, this isn't like really physics. It's Schrödinger's cat explain how this could look in the macro world. Right? And by the way, when you open the box, you are now entangled with what's going on in the box. And so how this translates in quantum is it gives you this ability. So if we think about classical computing, what we're doing is we're inspecting bits and bytes. right? But now what we can do is we can expect quantum positions and entanglement. So we have this superposition. And one of the ways, again, there are all these analogies that like people use and then people yell at them for using. And then I think it's that's not a bad way to use it. And I don't mind getting yelled at by like PhD geniuses. I do it all the time. But the idea is you take two gloves and you put a left-hand glove in one box, you put a right-hand glove in the other box, and you mangle up the box and you send one box to Venus. Instantaneously, when you open the one box, if it's a left-hand glove, you know that the other box has the right-hand glove. And some people call it faster than the speed of light, but it's not using speed of light. But and Einstein called this spooky action at a distance. And it literally, that was his sort of Schrödinger guy. It drove him insane that this could work. So this entanglement, and by the way, entanglement is like an interesting property that now they're using for encryption. So there's like really, it's like teleportation. There's just really interesting ways that now they're rethinking encryption using entanglement. But I'll run out of time if I go there. So the way that superposition and entanglement work in a quantum coding construct is that you use new type of quantum gates, which I could incorrectly say are new type of Boolean operators, but they're not really. But some of them emulate Boolean operators, but they expect this qubit entanglement and superposition. So now I logically build algorithms around this idea that two particles could be entangled and they could be in multiple states. This is where it gets really hard. It's not easy to write quantum algorithms. It's probably the hardest problem. And so so if you want to make my wife chuckle, ask her why I would tell you not to use Bracket from Amazon for testing this, all right? And she'll tell you the story how we've gotten John, why have we gotten this $100 bill for a year? Because I forgot. It's not only when you turn it off, they still charge you. You have to delete the whole thing. So stay away from Bracket. Because by the way, IBM's QuizKit is brilliant. It's easy to use. And it's kind of fun because I can talk theoretically all day, but you go in and start building these what they call C-knots and H-gates. So H-gates create superposition. C-knots create the sort of entanglement. Like if the first bit is on, it turns the entangled other qubit off, that kind of stuff, right? So again, it becomes this really sort of circuitry, algorithmic way to make these incredible algorithms. And so another part of entanglement that is sort of important to understand is what they call interference. So think about two pebbles in the water. So these are sort of wave functions, and not really waves, but again, waves are a good analogy to explain all this. You put two pebbles in there, and there's sort of one just about a half second for the other one. So the waves start colliding, and some of the waves amplify, and some of the waves sort of collapse or cancel, right? That's an easy thing. Well, that's basically what you're doing with quantum algorithms. And what's happening is the ones that have the highest amplitude is the highest probability of the answer. Yeah, it's definitely sort of weird, but the idea is you sort of, instead of sequentially saying if this, well, let me go to the next slide. So I think another one I don't mind getting yelled at by quantum physicists and mechanics and all that is the maze. So in a classic computing, I would use some algorithmic way, it didn't go this way, I might do backtracking, I might use parallelization, but in a sense, I'm doing a lot of sort of sequential operations. The way a quantum algorithm would find out the way to get out of a wet maze would be just send multiple waves to it. And the ones that sort of amplified itself the most were the most probable answer. So when it collapses, you get one answer, and then you can calculate the amplitude from that answer. And I'm really oversimplifying it. A, because if I didn't know, everybody'd leave the room, and B, I probably couldn't go too much deeper. But hopefully that makes sense. Think about now a financial algorithm that has hundreds of millions of variables that I could throw into this idea of a wave function and have it collapse and get the highest probability answer with one fell swoop. That's why you get from billions to weeks. So the measurement argument is sort of interesting. I'm going to have to go a little faster. it was funny, there was sort of two camps, right? There were people that said, kind of like, shut up and calculate, the math works. And then there were ones like Einstein and people and Schrödinger, and then other people who were like, no, there's got to be an answer. I'm like, I can't accept this. God, Einstein said God doesn't play dice, right? But the math definitely works. Like the transistor was created from quantum. And by the way, the transistor was probably the most important invention in technology that's happened in our life. It wasn't cloud, it wasn't agile, it wasn't DevOps, it wasn't, it was the transistor, right? And I've written some papers about the history of the transistor, right? And by the way, you know what the next biggest transistor is going to be? It isn't cloud and agile, it's going to be, when we get to sort of whatever this mythical quantum supremacy is. It'll be at that level. And Schrödinger was basically making a complaint, right? That's the thing. The Schrödinger's cat was not his endorsement. It was literally, this is absurd. Look at it from a world which should get everybody's attention, and this is why I'm disturbed by it. And so there are these interpretations, and this is the rabbit hole. This is why it's going to take me forever to write this book, because with the history of AI, it was sort of easy because I knew what to shade off. I could say, that's a good story, but I don't need to put it here. But in quantum, I don't know what I don't know. And one of the biggest rabbit holes in quantum, which is fun, is going down all these interpretations where you start that just wasted a month on that interpretation. But the most popular one is called the Copenhagen. And it really is, at a high level, the expression of the Schrödinger's cat. In other words, there's superposition, there's entanglement, you open the box, the cat is dead. Right? And again, it's a gross overstation, but that's the point of this presentation. And then Einstein was more concerned about, so Einstein, in the quick version of the history, Max Planck created the sort of Planck length, which defined the thing called the quanta. That was the thing that Einstein used to get his first Nobel Prize on the photoelectric effect. There's a lot more there to uncouple. And then Schrödinger creates this equation and creates the wave function as the math, basically, how to do this, right? So Einstein, again, was very concerned about entanglement and created the EPR paradox, where he spent a lot of his life trying to say, this doesn't make sense. That idea that the glove on Venus, what it is instantaneously, sort of defies everything that he tried to define, right? The speed of light. And so, but this is where it gets even crazier, right? I'm going to need a couple extra minutes, sorry, but I won't go too far. Chris is can I get a cheer for Chris? This guy is freaking awesome, honestly. I don't say that because he's my friend. I mean, he puts in a lot of freaking work. He didn't make any money off of this stuff. And people don't really appreciate how much burn time he puts into this community. Anyway, I digress. Would you get into these other really weird interpretations, which are fascinating, but for my book, is stay away from that. But I figured I'd tell them anyway. The many worlds is the idea that every time you open a box, there's a parallel universe. So you might open the box and the cat's dead. You might open the box, the cat's alive. Right? But that's the so many worlds. But that's pales into this one. And this was a good couple of weeks of wasted my life, is the participatory interpretation. Now, get this one, all right? So here's the deal. I think you're with me right now. Is everybody sort of with me? I mean, honestly, right? Okay? All right, yeah, fair enough, all right. So this is the one that really freaks me out. And if I was 20 years old, I'd drop everything. I'd go back to university. I'd get this is where epistemology meets physics, in my opinion, or metaphysics, or whatever you want to call it. But this is not that the cat is both dead and alive till you open the box. Grab your armchairs. The cat doesn't exist until you open the box. All right? Or there's nothing in the box until you open it. That means consciousness. And there's a whole thing about quantum consciousness. And again, there are dragons for rabbit holes. But that one freaks me out the most, is this idea that just thinking the consciousness itself creates reality. So this means that, all right, to cliche it, if the tree falls in the woods and nobody hears it, did it fall? Nah. The participatory version is, if the tree falls in the woods and nobody hears it, the tree never existed. I don't know. That freaks me out. So, but here's the thing. Everybody agrees on the math. It's the thing they disagree is, what happens when you open the box. And so that's why the experiment is so cool. It's not like with a cat, oh, you cruel, hating cat beast, right? It is this, like, opening the box is what literally smartest people on the planet, or some of the smartest people on the planet, have struggled with their whole life. And so there's this, like, mecca of ontology conversations. Like, what is a wave function? Why do we call it a wave? It's not a wave, right? Like, there's does measurement create the outcome? Like, what's going on there? There's, what is collapse? Is it real or is it not, right? The quantum state, the not only the many worlds, but the participatory, right? So there's really interesting, which are like, waste of time from my quantum computing history book, but hey. So, all right, I got 2 more slides. I might actually finish on time, Chris. I think, so 10 years ago, I heard about, my friend started a quantum computing company 10 years ago. He's actually one of the pioneers of what happened before DevOps started. We used to run this bar camp ESM. His name's Worley. He's a fascinating person. So I'm like, oh man, if Worley's doing this, I better like check into it. And I went to this sort of financial think tank thing, and there were a bunch of quantum experts, and I'm like, my son's going to college in a couple of years, and should he get into quantum? And they're like, no, stay away from quantum. This was 10 years ago. Like, it's never going to happen, 40 years. And I thought, you know what? Like, at the time, I was like 58 years old, 57 years old, like, if they're saying 30 years, like, I probably should stay away from it. And then I was thinking last summer about, like, what's my next book going to be? All right. Go deep, John. The history of quantum. I had so much fun writing the history of AI. I'm like, this has got it. And I looked and I saw the Niels Bohr and all these amazing stories. So that's what I do. I first see if there's any great human stories. Because I love the human. I try to think, like, how would Michael Lewis write this story, right? It's a storytelling, nonfictional storytelling. And so I started digging in. I'm like, this is kind of fascinating. Then I went to the IEEE quantum code, and then I was like just blown away. And I think if you listen to some people, now, most of the people have sort of like, they have the stakes in the game, so it's 2030 going to happen, prepare, right? Like, yeah, maybe. Maybe not. Maybe it's 2040. I don't know. But this will be, I'd agree, will be the biggest, not only the biggest technological revolution in computing, it will be I think it will be the biggest technological revolution. Now, it can be challenged on that, but I think not the biggest, it will be the biggest since the transistor. So why is this in a DevOps conference? Why is this crazy guy talking about quantum who isn't a scientist, who's talking about dead cats? Because here's what the world is probably going to look like. And I'm going to stick the landing, folks. I'm telling you right now. That the world is not just going to be what they call QPUs. Chris mentioned this yesterday, right? There's going to be QPUs. And they're going to get the fault tolerance, and they're going to get the million qubit stuff solved. They're going to. There's too many smart people working on it, putting too much money in it. And if we don't, China will. Then around that are going to be GPUs. They're not going anywhere. And we're still going to have CPUs. So the new data center, there's 2 meta points out of this. One is the new data center is going to be this weird network structure of CPU, because CPUs didn't go away when GPUs came, right? We're not all GPUs. In fact, proper inference really is more CPU than building models is almost exclusively GPUs. Well, GPUs are not going away when QPUs come. In fact, I'll give you one use case to end this presentation on. But one of the points I want to make before I give you like this, I think, really interesting use case, which is a quantum neural network structure, is this, if you're young right now and you like doing DevOps, this is going to be an incredible opportunity to manage the complexity of a network that is made up of this stuff. I mean, think about how hard it is to do. Have any of you working with GPUs in a large infrastructure right now where the complexity is not only networking, but DevOps are really hard? That's baby cakes compared to what's going to happen when you integrate all 3 with GPUs. All right, so one last story, and I'm out of here to lunch, and don't forget to go say hi to my wife. Quantum neural networks. So what's interesting is one of the hardest problems. So I spoke to a young man at JP Morgan Chase who was head of sort of financials, running optimization, not crypto, for their financial modeling, focusing on quantum, right? And I asked him, what are the really hard problems? And he said, the hardest problem, John, is humans writing quantum algorithms. In other words, it's kind of, even the smartest people on the planet are having, and this is what they told me 10 years ago. It was the hard part is actually writing quantum. So one of the ways quantum neural networks are working is, why don't we use a neural network, a deep neural network, to help us build? Maybe humans aren't smart enough to build quantum algorithms, so we use neural networks to help us figure out these really hard problems, to create these kind of CNOT and H-gates and all this stuff, right? Because neural networks are pretty good at creating code. If you've heard anything about Opus 4.6 and Mythos with the adversarial stuff, they're pretty good at figuring out really hard problems with code. That's the ingress. And then the egress of a quantum neural network is, what if I threw in, let's make up a number, 1 billion variables into a financial model in a quantum algorithm, and it came back with like what humans would look at and say, have no freaking idea what that is. But you know what's in there is patterns. So what if I took those patterns and folded into a neural network and say, neural network, can you just highlight what the patterns might be? And those are two things that are going on in quantum neural networks right now. So there's an ingress, algorithm, and there's an egress of, so that's a beautiful combination of this kind of structure. So we're going to see all that kind of stuff. Anyway, thank you so much. I definitely want feedback. I'll probably do an open spaces and much more than this. I can just give you sort of anecdotal data of like what I'm seeing and all that. But I would love to hear like, John, I think you're the better on this, or I had no freaking clue what you were talking about. All right, thank you very much, y'all.